Welcome to this lecture on partial differential equations. Today we are going to explore a fascinating physical phenomenon, heat conduction in solids. Have you ever wondered why a metal spoon gets hot when left in a pot of boiling soup, even if the handle isn't touching the liquid? By the end of this video, you will understand the exact mathematics that govern how thermal energy travels through solid objects. Before we dive into the equations, let us understand why this concept matters. Heat conduction is the fundamental process where thermal energy moves through a solid material, from a hotter region to a colder region. This happens because rapidly vibrating hot atoms bump into their cooler, slower neighbors, passing the energy along like a microscopic relay race. Unlike convection, there is no visible movement of the material itself. The fundamental rule governing this invisible transfer of energy is known as Fourier's law of heat conduction, which states that heat always flows downhill, from higher to lower temperatures. Now that we understand what heat conduction is, let us look at the mathematical engine that drives it, the one-dimensional heat equation. This formula comes from combining Fourier's law with the principle of conservation of energy. In this equation, U represents the temperature at a specific position x and time t. The term alpha squared is the thermal diffusivity, a constant that measures how quickly a material reacts to temperature changes. If alpha squared increases, heat spreads much more rapidly through the material. The equation beautifully states that the rate at which temperature changes over time is directly proportional to the concavity of the temperature profile. Before we prove where this equation comes from, let us see it in action with a concrete example. Imagine a metal rod that is 10 centimeters long. The left end is permanently held in boiling water at 100 degrees Celsius and the right end is in an ice bath at 0 degrees. We want to find the temperature at any point along the rod after a very long time has passed. Because we have waited a long time, the temperatures are no longer changing. This means the system has reached a steady state. So the derivative of temperature with respect to time is exactly 0. Continuing with our steady state problem, we set the left side of the heat equation to 0. Since the thermal diffusivity is a non-zero constant, we can divide it out, leaving us with the second derivative of temperature equal to 0. Integrating this twice with respect to position gives us a straight line equation with two unknown constants, C1 and C2. To find these constants, we apply our boundary conditions. At the left end, where position is 0, the temperature is 100. Plugging this in immediately reveals that our second constant, C2, must be exactly 100. Now we apply our second boundary condition to finish the problem. At the right end of the rod, where the position is 10 centimeters, the temperature is 0 degrees. We plug in 10 for the position and 100 for C2. Solving this simple algebraic equation shows that C1 is negative 10. Substituting these constants back into our general equation gives us our final formula. Physically, the negative sign tells us that the temperature drops by 10 degrees Celsius for every single centimeter we move away from the boiling water, creating a perfectly linear temperature profile. Now that we have successfully used the heat equation, let us understand exactly where it comes from. We will derive it by examining a tiny microscopic slice of our metal rod located between position x and position x plus delta x. First, we use Fourier's law to find the rate of heat energy entering the left side of our slice, which we call Q1. Then, we write the exact same expression for the heat leaving the right side, Q2. The net rate of heat accumulating inside the slice is simply the difference between the heat entering and the heat leaving. To make this derivation perfectly clear, let us visualize the microscopic slice we are analyzing. Here you see the one-dimensional metal rod aligned along the x-axis. The shaded region represents a tiny slice of width delta x. The red arrow shows heat energy, Q1, entering the left boundary at position x. The blue arrow shows heat energy Q2 leaving the right boundary at position x plus delta x. If the red arrow brings in more heat than the blue arrow takes away, thermal energy builds up and the temperature of this specific slice will rise over time. Returning to our derivation, we now look at the accumulated heat from a different perspective: energy storage. The rate at which thermal energy changes inside the slice depends on the material's specific heat capacity, its density, and the volume of the slice. By the law of conservation of energy, the rate at which energy is stored must exactly equal the net rate of heat flowing into the slice that we calculated earlier. When we set these two equations equal to each other, we notice that the cross-sectional area appears on both sides, meaning we can cancel it out entirely. This brings us to the final result of our derivation. We divide both sides of our balanced energy equation by the volume length, delta x. The right side now represents the difference between the first spatial derivatives at two closely spaced points, divided by the distance between them. As we shrink our tiny slice down so that delta x approaches 0, this fraction perfectly matches the formal mathematical definition of a second derivative. By grouping the material constants into a single term called thermal diffusivity, we arrive at the famous one-dimensional heat equation. The derivation is complete. So, we have proven that the heat equation holds true. This brings us to a more complex scenario. What happens when the temperature is actively changing over time? In our previous example, we waited until the rod reached a steady state. But if we want to know exactly how a rod cools down minute by minute, we cannot set the time derivative to 0. Instead, we must use a powerful mathematical technique called the separation of variables. This method allows us to break a complex partial differential equation into two simpler ordinary differential equations that we already know how to solve. Let us look at the core assumption behind this new technique. The separation of variables method guesses that the final temperature function can be split into two completely independent pieces. We assume that u of x and t is equal to a spatial function, capital X, multiplied by a temporal function, capital T. While this might seem like a restrictive guess, it is incredibly effective for linear equations. If we substitute this split guess back into the heat equation, the partial derivatives will only act on their respective variables, allowing us to separate the math into a space part and a time part. Let us apply this method to a time-dependent cooling problem. Consider a metal rod of length pi with a thermal diffusivity of 1. Both ends are kept packed in ice at 0 degrees. Initially, the rod is heated, so its temperature profile forms a sine wave. We need to find the function describing how it cools over time. We substitute our separated guess into the heat equation and divide by the product of x and t. This puts all the time variables on the left and all the space variables on the right. They must both equal a negative separation constant. Continuing with our separated equations, we first tackle the spatial part. Rearranging the right side gives us a classic harmonic oscillator equation, whose general solution is a combination of sine and cosine waves. We must apply our boundary conditions to see which waves fit inside the rod. The temperature at the left end is 0, which eliminates the cosine term. The temperature at the right end is also 0, which tells us that the constant k must be a whole integer. Looking at our initial sine wave profile, we can see it perfectly matches the case where k equals 1. Now we turn to the time-dependent part of our separated equation. We substitute our known value of k equals 1 into the left side. This leaves us with a simple first-order linear differential equation that describes exponential decay. Solving this equation gives us an exponential function with a negative exponent. This makes perfect physical sense. It tells us that as time moves forward, the temperature will shrink towards 0. The rate at which the temperature drops is directly proportional to the current temperature, which is exactly how cooling works in the real world. We are ready to assemble our final answer. We multiply our spatial sine wave function and our temporal exponential decay function back together. Finally, we use our initial condition, where the starting temperature was 5 times sine of x, to determine that the combined arbitrary constant must be exactly 5. This final formula tells a beautiful physical story. The temperature profile keeps its smooth sine wave shape at all times, but the peak of that wave flattens out exponentially as time passes, eventually cooling the entire rod down to 0 degrees. We have covered a tremendous amount of ground today. Let us review the key takeaways. First, heat conduction is the transfer of thermal energy driven by a temperature difference, governed by Fourier's law. Second, the one-dimensional heat equation balances this heat flow with energy storage to predict temperature changes. Finally, by using techniques like steady-state analysis and separation of variables, we can solve this equation to model real-world cooling. You now have the mathematical tools to understand how heat flows through any solid object. Excellent work!